we'd like to introduce you to Hongli.
Yes. So Hongli has been he's a creator of Passenger. You potentially know that. I think it's nice. It made a lot of things possible for me as a Ruby developer. So I'm quite thankful for that. But also nice. He recently asked the community on some input on a memory optimized Ruby distribution a few weeks ago, and then people, I think it was Hacker News, responded to it, well, you should take a look at Ruby Enterprise Edition. So that last version was for Ruby 1.8.7, so that's history. And he had to remind the audience that he was the creator of that thing. So he cares about memory optimization already for quite some time.
Yeah,
so,
oh, sorry.
Yeah, no, go ahead.
No, he also knows a little bit of Japanese that he learned from anime. So I guess when it comes to pirates and ninjas, you fall more on the ninja side of things. Is that right?
I don't know. Maybe I can speak with Mats a little bit in Japanese if I'm lucky.
There you go. So, well then, take it away.
Thank you. It's a great pleasure to be here. Yeah. What causes memory bloat? As the author of Passenger, I've had to deal with this issue for quite some time. But first, let me say something, and that is that this talk will be a little bit different. So some people may have already seen my talk or read my blog about the subject. And is this talk just a reiteration? No. I have made some surprising new discoveries lately, which I will talk about during this presentation. And some new discoveries were made as late as Monday on 1800. Well, I also had a deadline for submitting this talk to EuRuKo so that they can live caption it. So I was working like crazy for the past week to rush. Well, you can imagine how busy I must have been. And at the end of the talk, I will also have a nice announcement. Well, it's not a surprise anymore for some people, but still worth talking about, so stay tuned. So at Fusion, we have a proxy server written in Ruby, and it serves Debian and RPM packages. The server doesn't do much. It's literally just a proxy, makes a call to another server, and then returns the result with some slight modifications in the headers. And then I noticed that the application's memory usage would balloon to 1.3 gigabyte over time. And I thought, well, this is crazy. It's just a very simple Ruby application in less than 1,000 lines of code. And there's no reason why it should use that much memory. It couldn't possibly have a memory leak. So why is the memory usage growing that much? I have heard rumors before about Ruby memory bloating and their causes. In fact, Ruby speed consultant and Puma maintainer Nate Bergelbeck, as well as EuRuKo, they both have write-ups about this issue. They basically state that memory bloating is caused by memory fragmentation, and there are two proposed solutions by them. You either set a magical environment variable, or you override the operating system's memory allocator and use a custom one called jemalloc. So I implemented what they said, and then my memory usage was reduced by more than half. The end. Any questions? No. If only it was that simple. Their solutions indeed work, but I read the explanation of why it happens, and then something just fell off. Based on my understanding of how memory works, their explanation seemed a bit incomplete. And so I started researching. And in this talk, I will be talking about three things. First is, how does memory allocation work? The very basic concepts. Second one is, why does this bloating happen? And then third one is, what can we do about it? And one important thing to mention is that this problem that I'm describing, it only manifests itself in multi-threaded Ruby apps and only on Linux. So it doesn't happen on Mac, it doesn't happen on FreeBSD, and if you do run on Linux, if you don't use threads, then you also don't see this problem. But it's kind of ironic because multi-threading is supposed to give us more concurrency with little added memory usage. And I should also note that Ruby is not the only issue, the only application that suffers from this issue. For example, Redis also had this issue. Other kinds of servers also had this issue. So it's not entirely Ruby specific. Memory allocation 101. Let's begin with the basics. The operating system comes with a library called the memory allocator. And this component is what keeps track of what memory is in use and what is available. It has a very simple API. The malloc function allocates a piece of memory of the requested size, and then it returns the memory address of that allocation, or it returns an error. The free function frees the memory piece that was allocated at the given address. But the memory allocator actually consists of two parts that work very differently. One is the application side called user space, and the other one is the OS kernel, so the Linux kernel in this case. The Linux kernel is the closest to the hardware. The memory allocator is a library in user space, and it calls a kernel API to actually allocate memory from the hardware. The kernel can only allocate memory in blocks of 4 kilobytes, and such a block is called a page. There are also other unrelated things that are called pages, so for clarity I will use the term OS page. The OS can only allocate or free memory in units of entire OS pages. And the reason for this is complicated, so I won't go into the details, but suffice to say that this is a fundamental property of all modern kernels. The user space memory allocator can be used to allocate memory pieces of any size. So how does that fit with the constraint that the kernel can only allocate in 4 kilobyte blocks? Well, it does something smart with that. And there's also the thing that asking the kernel to allocate memory is an expensive operation, so you don't want to do it too often. The memory allocator allocates large pieces of memory from the kernel and then defies those pieces in smaller ones to serve its own callers. So here's an example interaction. An application, for example, Ruby, asks the memory allocator to allocate something, and then the memory allocator asks the kernel to allocate something that is usually much bigger. So the kernel gives back a large bag of stuff, and then the memory allocator will divide parts of that for its own callers. What is allocated from the kernel is called a heap, and likewise there are also unrelated things that are also called heaps, so I will use the term OS heap for clarity. So the memory allocator carves out a piece of the requested size from what is allocated from the kernel and then returns its address to the caller. And as long as there's still space left in an OS heap, the memory allocator will continue to carve out free spaces from it, and only when it is full and no new allocation requests can be satisfied with an OS heap will it allocate a new OS heap from the kernel. So that's it for memory allocation 101. But things are actually more complicated because on the Ruby side, Ruby manages its memory in its own manner. So there are Ruby objects, and Ruby does not allocate each object separately. With an object, I mean a string, an array, or even a class or a regex. Those are all objects, and it is very expensive if you call malloc on each object separately. That also has a large space overhead and a large time overhead, so you don't want to do that. And instead, Ruby Ruby uses a strategy similar to what the memory allocator also does, and that is it will request memory from the memory allocator in large groups. And in this case, a group that is allocated by Ruby is called a Ruby heap page, which, by the way, have got nothing to do with OS heap or with OS pages. A Ruby heap page is split into equal-sized slots, and one Ruby object occupies one slot. Whether it is a string, an array, a class, or any other objects, it occupies one slot. Some slots could be as of yet unoccupied, and Ruby stores any new objects in there. A slot is about 40 kilobytes, and most Ruby objects fit in there, but not all of them do. For example, if you have long strings or long arrays, what do you do if that string is larger than 40 kilobytes? Well, it is stored separately. It is allocated separately from the memory allocator, and then in the object slot, there will be a pointer to that separately allocated data that is larger. And if the object is destroyed by the garbage collector, then not only is that slot marked free, but also any external data that was pointed to by that slot will also be freed. So to sum up, there are roughly two types of memory in a Ruby process. First, there are Ruby heap pages with their slots and Ruby objects. And second is memory stored outside of Ruby heap pages. And all that memory was allocated from the memory allocator library. So here I have a question for the audience. I have a memory benchmarking program that does nothing but allocating memory in a loop. After a while, memory usage balloons to 230 megabytes. And the benchmarking app is multi-threaded. So here's a question. How many percent of the 230 megabytes belongs to the left side, and how many percent belongs to the right side? This is a multiple choice question. Who think it looks like scenario A, where most of the memory is occupied by the left side? Put up your hand. Who thinks it's like 50-50? Put up your hand. And who thinks it's like it's like C? Okay, the majority of people think it's like C. Are you confident? That was a trick question. You have all been fooled. There is a third category that turns out to be the majority of the memory usage in my benchmark application. Okay, let's sink in for a bit. My benchmarking application uses 230 megabytes, and Ruby knows about 7 megabytes. So the 7 megabytes is all the Ruby objects, all the Ruby heap pages, as well as any external data that each object points to, so including string contents. All of that is only 7 megabytes, give or take. And yet, the operating system memory measurements tools tell me that the process uses 230 megabytes. So that red category in the previous slide, it's very, very big. What is this? It's insane. It's something that Ruby does not control. Okay, so people in the past tended to blame Ruby for being memory inefficient, or that it doesn't compact memory. Well, some of them might there's some truth in that, but it looks like for quite a large part, it's not Ruby's fault. So it can go free, I hope. But what is going on? Where does the memory bloat actually come from? Let's go back to the magical solutions that Nate and EuRuKo suggested. Why do they work? This environment variable, for example, reduces memory usage significantly. What does this variable do, and why does that help? Well, I dived into the documentation of the memory allocator, but also the source code to figure out what it does, and here's a summary. It has got to do with multi-threading. When multiple threads try to allocate memory from the same OS heap at the same time, they contend for access. Only one thread can perform an allocation at a time, because otherwise it will not be thread safe. But if you do that, then you also reduce multi-threaded memory allocation performance. So the writers of the memory allocator, they come up with a solution for that in order to improve multi-threaded performance. The memory allocator tries to create multiple OS heaps and tries to assign different threads to its own OS heap. And most of the time, a thread only needs to work with that particular OS heap, thereby avoiding contention with other threads. In fact, the maximum number of OS heaps allocated in such a fashion is by default equal to 8 times the number of virtual CPUs. So suppose I have my humble MacBook with two cores and 2 hyperthreads each. That's 32 OS heaps if I were to run Linux on that laptop. Okay, so there are lots of OS heaps. So what? Why does that necessarily lead to more memory usage? One would expect that with more OS heaps, each OS heap is less heavily utilized. So there should not be that much difference in total memory usage. It's like you have a bucket of water and you divide that water in multiple buckets, but it's still the same amount of water. Well, to further research this, I had to gain a better understanding of how the OS heaps look like. Maybe it's in the way that they are internally organized that causes memory bloat. Unfortunately, there are no tools that allow me to inspect OS heaps in such a manner. So I wrote my own. First, I had to dump the layout of the OS heap somehow, and I was kind of forced to dive into the memory allocator source code to figure out, okay, what does it do? How does it lay out memory? And then next, I wrote a library that traverses those data structures and writes the layout to a file. And then finally, I wrote a tool that takes such a file as input and then compiles a visualization in the form of HTML and PNG images. And then it looks like this. Here's a visualization of one particular OS heaps, and there are multiple OS heaps. You see that you see small blocks in this visualization. Those represent the OS pages. Red areas are memory locations that are in use by the memory allocator. Gray areas are free locations, but not released back to the kernel. So those are locations that are part of OS heaps that have not been given back. And you don't see any white blocks here, but white blocks do exist. White means that that location is not allocated by the kernel, so it is fully free. And well, what does this tell us? First, there is fragmentation. You see that the red spots are scattered, and some OS pages are only half red. So for example, this one, only a tiny bit of red, but the rest is gray. That is fragmentation. An OS page that is only partially occupied still uses 4 kilobytes. So there's some memory waste there. And yeah, some people blame fragmentation as the cause of memory bloat. And second, most OS heaps look like this. There's a significant number of entirely gray OS pages without any red inside. In fact, I would say that the entirely gray blocks form the majority of this visualization. And I also compared the visualizations between a normal run and a run with malloc arena maxis 2, that magical environment variable that would reduce memory usage. What is the difference? Well, the visualization of the latter reveals a lot less gray. Almost everything is red. But why is that? Why is there such a big difference between the two scenarios? Well, it's like this. The gray OS pages are not released back to the kernel because they are reused by the memory allocator to satisfy future allocation requests. I talked about how that it is expensive to allocate memory from the kernel, and so the memory allocator will try to cache these things and keep them around for later usage. If you set malloc arena maxis 2, then a lot of the gray OS pages, they get reused, and so you don't get a lot of waste. With a normal run, because there are so many OS heaps, the chance that an OS page gets reused becomes lower, and so there is more waste. But what can we do about this? I researched the memory allocator's source code a bit more, and it turns out that by default, the memory allocator only releases OS pages back to the kernel at the end of an OS heap, and even that is done occasionally. But that's not good, because as we saw in the visualizations, lots of those gray blocks, they are somewhere in the middle, definitely not at the end. But I found a magic trick, and there is an API in the Linux memory allocator called malloc_trim that forces it to release gray blocks back to the kernel. What happens if we modify Ruby to call this function during garbage collection? Well, the result is profound. Memory usage becomes almost as low as setting malloc arena max is 2. And here's the visualization. You can see that a lot of white holes have appeared where previously they were completely gray, and that is the source of the memory usage reduction. So in conclusion, fragmentation turns out to be, at least for a part, a red herring. It is an issue. There is still something to be gained by reducing fragmentation, but it looks like most of the memory is actually just wasted because the memory allocator doesn't like to feed things back to the kernel. The solution turns out to be super simple because it is literally one API call from the Ruby garbage collector. It's a one-line patch, but yeah, just finding the solution, it took a lot of research time. By now, a number of third parties have already tested my finding in production-like environments. They have observed 17 to 20% less memory, but also a 7 to 20% performance drop. So that call is definitely not free. Your mileage may vary. It depends on your workload. And there's still room for optimizations. For example, we can choose to call that API call less often, or maybe over time, or something like that. So there are ways to amortize the performance impact of this call. And third parties have also observed that using the JEmalloc memory allocator library is still better. JEmalloc uses a more complex algorithm than the built-in Linux memory allocator, and it lays out memory in a different way, in a way that is that results in less fragmentation, but also less maximum memory usage and less waste. So if you use JEmalloc, you can potentially get less memory usage and a performance win. But there are also problems with that because it's a much larger dependency. You need to be wary of which versions you use, and also the way you activate it will affect how much effect it has on your application, and a bunch of other issues. And well, we're still not done researching because earlier this week I stumbled upon a nice surprise. I was researching JEmalloc, and then I discovered that I can actually combine JEmalloc with malloc_trim. Somehow that had some effect, and it didn't make any sense for me because if JEmalloc is in use, why would this still have any effect? Well, the reason behind this was because I was compiling Ruby with the ---- with JEmalloc build flag, but that only activated JEmalloc. It was only half effective in activating JEmalloc, so the end result was a Ruby installation that used JEmalloc partially and the system memory allocator partially. It is something that I will need to think about how to solve this, and it looks like I will have to use the LD preload mechanism, but that has its own problems. Well, researching is fine, but I also want to bring value to the Ruby community. Like, I'm also a very pragmatic guy, and if I see opportunities for optimization, I want people to be able to use this. JEmalloc and other kinds of optimizations, they have been around forever, but they are not officially incorporated in Ruby for good reason, because there are risks attached to it. But I think that for some people, maybe they are willing to take some risk in order to get a large benefit. So I think a lot of people are thinking, okay, when can I make use of this, of these optimizations? And what is the easiest way to make use of this? Because right now, you have to compile Ruby from source in order to make use of this, and that is a big hassle. Nobody wants to do that. I don't want to do it either. Well, this is what I just talked about. So, here's the announcement. Together with Full Stack, I am working on a new Ruby distribution whose goal is to package all this memory reduction work in a form that is easily usable by users. And we call this distribution Full Stack Ruby. So it'll be faster, use less memory, and we do this by incorporating jemalloc and malloc trim. We distribute binaries, not source, and we distribute them in the form of Debian packages and RPM packages, so that you don't have to compile, and we integrate with the OS package manager so that you can also get security updates that way. And I have understood that just keeping Ruby security patch, if you compile it from source with rpnf install or rpm install, that's also a huge hassle. Now, this is still in beta. We got an MVP out yesterday, so there's still a lot of room for improvements. In the future, we will even supply Docker images and provide EuRuKo support. And you will be able to, so the apt and yum repository isn't there yet, but it will be. Right now, it's a bunch of Debian and RPM packages, files that you can download from GitHub, but we are working on apt and yum with high priority. If you're interested, please take a look at our roadmap on GitHub to see what we have in store. It's 100% open source, and we welcome contributors. So we're not going to make money out of this. There's not going to be a paid version. This is a community project. So check out its website. There's an FAQ section. So if you have any questions about, hey, well, what about vendor login? That is probably the biggest concern I have heard from people. Check out the FAQ. I have some answers written there. Full Stack is a technology partner company in the Netherlands, and they are chock full of experts, like this guy. This is Pieter Lange, who is also in this building, and he's probably the best Kubernetes and DevOps expert in the Netherlands. It's just amazing how much he knows. He's helping me so much with the infrastructure for this project, which is not trivial, because we need a high-performance CI pipeline to generate something like 70 to 100 RPM and Debian packages and Docker files for each release for multiple distributions. And they're supplying bandwidth and that sort of thing. So if you see him, please shake his hands. He's awesome. Oh yeah, and this goes especially to Charity Mayers, because Peter is a huge fan of you, Charity. If you see him, please give him your autograph. So thank you, and please follow my blog for updates, or check out Full Stack Ruby.
Thank you, Hongli. That was wonderful. You could say it brought me good memories of the sea.
Oh, thank you.
No, that was great. Thank you so much, Hongli.